Assalamualaikum everyone. We're excited to present our final year project, NeuralTrace Smart Memory Assistant. This project was developed by a team, myself, Muiz Zulfikar, who's our team lead, along with Abdullah Maqsood and Anfa Majid. So let's dive into what NeuralTrace really is and how it aims to make a real difference. NeuralTrace is a smart assistant built specifically for people who suffer from memory loss, like those with dementia or Alzheimer's. The idea is to give them back some independence while also reducing the stress on their caregivers. Here's what it can do: recall memories using voice and images, find misplaced items using camera-based object tracking, send reminders for important tasks and medicine, and also alert caregivers when a person enters an unsafe area using geofencing. It works through a mobile app, and we also plan to integrate it with wearables like smart glasses or headphones for hands-free support. So let's go over the problem statement a little bit. People with memory issues struggle daily with forgetting important conversations or appointments, misplacing personal belongings, sometimes walking into dangerous places alone. The tools available today don't really help in real time or provide much context. On top of that, caregivers, often family members, go through a lot of mental stress, having to constantly supervise. So our goal was simple: build a system that helps the person on their own while giving caregivers a peace of mind. Now, our application is divided into four core modules. The first is the audio analysis, which converts spoken conversations into text, pulls out important information like appointments or tasks, let the user ask, "What did I say earlier?" and then it gets an answer. Uh, the second one is object detection, which uses the camera to find misplaced objects like the keys or remotes, gives both visual and spoken feedbacks to guide the user. Location mapping is the third module, which understands the layout of the home, tracks object placement and user movement, triggers alerts if someone goes outside a safe area. And the last one is the caregiver supervision, which sends alerts like user left the house, and it also allows caregivers to remotely monitor tasks and medicine. And we ensure privacy using role-based data access in this caregiver module. And each module handles a piece of the puzzle, from remembering what was said to finding what's lost to keeping the user safe. Now let's go over the technical architecture of our system. We've organized the system into three main layers: the presentation layer, the application layer, and the data layer. So the presentation layer is for to capture the user input. This is where the user interacts with the system. We have audio and video capture modules. These take in what the user says or sees. There's also a text-to-speech module to speak back to the user and give any answer to their queries. For example, if the user says, "Where are my keys?" the audio is captured here and sent to the next layer. Now let's go to the application layer, the brain of the system actually. This is where all the smart processing happens. It's divided into two layers. The processing layer, at the processing layer, the audio is basically, the audio is cleaned up and converted to text using speech to text. A query trigger decides what kind of request this is. It sends that to the right module, either for memory recall or object detection. The publisher layer, this layer looks at the user's request, processes the meaning, and sends back an appropriate answer. For example, if the user says, "Did I take my medicine?" it will check the history and say, "Yes, you did" at 9 a.m. Then we have the two smart AI modules: the audio analysis module, which handles the memory recall using past speech, and then there's the object detection module, which matches.
When we record audio from the front end, we send it to the back end and we immediately clean and pre-process this audio. In cleaning and pre-processing, we basically remove noise from the audio and bring it to the same base. This audio is then converted into text, and for each text we do dynamic data filtering and scoring. Basically, we find ratio of non-important words to important words and remove all sentences that are found to be non-important based on lexicon-based data scoring. These texts are then converted into chunks, and each chunk is converted into vector embeddings. These vector embeddings are then stored into vector database. Once a query comes in, we query the vector database to find the relevant chunk using vector search and Elasticsearch. The answer of Elasticsearch and vector search is then converted into one singular chunk, and this chunk is passed to the LLM with query to get a response. Once we have a response, we convert it into audio and send back to the user.
We start with an RGB image. Typically, a single frame is extracted from a video. First, I use YOLO to detect visible object. These detections are converted into 80-dimensional one-hot encoded vector that represent the presence of each object. Next, we construct an 80 by 80 co-occurrence matrix from this vector to capture all objects pairing. This matrix is then element-wise multiplied with a pre-computed discriminative vectors, which we build during training. to emphasize object pairs that are more informative for distinction between scene types. These weights were learned from a variance space analysis on the annotated Places 365 dataset. The resulting weighted matrix is flattened into a 6400 dimensional feature vector, which is then passed through a neural network that denoises and compresses it into a 256 dimensional object-centric feature representation. In parallel, I run the same input image through a pre-trained ResNet 50 to extract a 2048 dimensional feature vector. This captures spatial layout and texture-based cues that are often missed by objects-only features. These two vectors, the 256 dimensional object feature and the 2048 dimensional visual feature, are concatenated and fed into a Fusion network trained for indoor scene classification. The output is 14-dimensional software vector, and the highest scoring is selected as a scene label. Now, that's just for a single frame. In practice, the pipeline is applied on a video input coming from the front end. The video is broken down into frames at regular intervals and temporarily stored. Each frame is passed through this pipeline. Objects are detected and stored. Scenes are classified, and all results are indexed into a dictionary by frame. Finally, once we have classification from all sampled frames, we apply a majority voting mechanism across them. This ensures robustness by reducing the impact of outlier frames. And the most frequently predicted scene label is selected as a final scene classification for the video segments. And later on, we delete all the frames that were stored during this process.
We also have a location tracking module in our app that enhances patient safety through continuous background monitoring. A geofence defines the patient's area, and if they step outside it, an alert appears on their phone. At the same time, a notification is sent to the caregiver to ensure a prompt response. So now let's walk you through the app. First of all, we will create two accounts, one for the patient and one for the caregiver. So now we will enter all the details of the patient, and in the last three fields we will enter the geofence radius that we talked about in the last slide. So we can set the radius in meters and we can set the latitude and longitude using current location. So now we will create a caregiver's account. Now that the account is created, we will log in with the patient's account first. And as soon as the patient logs in, there is a notification that he gets, welcome to NeuroTrace. And then first of all he has to choose a caregiver, which he can choose from a list of the caregivers, and the location is continuously being monitored. And the caregiver, he can call the caregiver with a single click of a button, and he can also add reminders. He can choose the date and time of the reminder, and he will be reminded at that time. The patient can also mark a reminder as completed. And then we have some previous conversations that the patient had some days before. Now we will record. My name is Abdullah. I'm 22 years old. I have software architecture class tomorrow. Now when we will ask the assistant, it will answer us using the audio we recorded. Similar to audio, we also have a video recording option. Now after the video is recorded, it will be processed and the data from the video will be saved, and then we can ask the assistant questions regarding this video as well. So now let's ask, where is the laptop? So since we recorded the laptop on a bed, so it should say the laptop is in the bedroom. So here is the profile of the patient, and now we will log in with the caregiver's account, and the caregiver will be seeing all the patients that are linked to him. He will have their information, and in case there is some problem he will get the notification as well. So this is the profile of the caregiver which tells the preferences and permissions. So that's it. Thank you.